So now I briefly want to talk about memory. So obviously you need memory to store large amounts of data, programs, pictures, whatnot. First, a little bit of nomenclature. So if we talk about a 64 by 8 RAM, what we mean is that in this case, we have both addresses and data. So this 64 indicates the number of addresses, meaning it's the number of locations in which I can store data of a given size. And this 8 here indicates that I'm just storing a single 8-bit number in at each address. Size of the data per address. So examples, addresses and data are shown here on the left-hand side. So it's the address itself is a 6-bit number, and the data here is an 8-bit number. And RAM, of course, as you know, stands for random access memory. So I can read and write to that memory. And what I want to do in this brief video is kind of construct a simple RAM. I should also add that in this sort of high-level description, I'm also going to have one other input, write, which I can set either to 0 or 1. Then if it's 0, I'm storing data. If it's equal to 1, then I'm reading. Sorry, should do it the other way around. So if it's when writing is true, then I'm storing new data. When writing is false, then I'm reading data that's already stored. Good. So let's kind of construct a memory from the components that we've developed in class. So we're going to start with writing. So we want to put new information into our memory. So I'm going to use this decoder here. So if you remember, a decoder is an element that takes, in this case, a 3 to 8 decoder takes a 3-bit code as an input, and it sets one of 8 possible output values to be true, or output wires to be true, and all the other ones are false. So I'm going to use here, this is an enabled decoder, so I'm going to connect the write input to the enable input, so that determines whether anything is going to be written or not. The input that I want to go read in is drawn up here, so input 3210 is the number that I want to read in, and input 3 goes into one of these cells here, input 2 goes into one of these cells, input 1 goes here, and input 0 goes here. So what you have to do is, of course, use the decoder to select which row of cells you actually want to store this information in. So you have here, each wire is connecting across here. So each of these squares essentially is one memory cell, if you like. And there's some sort of enable input associated with each cell, such that if, for example, I'm choosing my controls A2, A1, and A0, these are my control inputs here, if they take the value 000, well, only this top wire here is going to be active, and I'm going to enable these memory cells to read in and store the information coming in. And all the other memory cells will just not do anything in this context, right? And obviously, as I change the code, I can load information into different cells. Now, a different question is, how can I actually get information back out of this system? So for that, I'm going to add one other set of components that we found to be very useful in various contexts. So these are the outputs here, and of course what I want to be able to do is I want to take a specific row of data, like one number that was stored together, and read it out specifically. So I need to be essentially pick data from one of these 8 cells in each column and put it into output. And of course the element or the component that allows you to do this is a multiplexer. So here I'm going to add a multiplexer for each row. Okay. The controls here are going to be A2, A1, and A0 everywhere. Right? And then of course the inputs to this multiplexer, so there have to be 8 wires coming in. These come from these memory cells. So every cell here is connected to this multiplexer such that I can read out by selecting a specific wire, for example 000, I'm just going to read the information from this, the data coming in from this cell, and going to copy it on the output. And of course the same is true on all the other cases. I'm not going to draw all of it, but you sort of imagine, well, it's kind of obvious how this is going to work. So you do the same thing for all the other ones, and so now you have a system that allows you both to write and to read. So again, if you write, you're setting the control, the enabler on the decoder to be 1. You're setting some value for this control input A2, A1, A0 that picks the row that you're going to write to, and into that row you're going to copy the number in 3, in 2, in 1, in 0. Then to read that number out, you're going to switch write to 0 so that the decoder is disabled, and you're going to choose whichever control input for your multiplexers. Again, if you want to read the first row, set all 3 values to 0, and that's going to take the data coming from this memory cell and just copying to the output value such that you can work with it. So this is actually a very simple architecture for a RAM. We're not going to dive into much detail into what these memory cells look like, but essentially the requirements are that you have to store 1 bit of data, and that you have to be able to change data based on an input when a specific row is selected, right? And the element that allows you to do this is essentially a flip-flop. So you have an input, a single flip-flop that you can read into the data. You can of course read the data out again, and now in this case here it's sort of an enabled flip-flop where the row select is connected to this enable. So if enable is true, then you're reading in new inputs. If enable is false, you're just holding the value that you're currently holding. As a sort of a use example, this is kind of nice. I mean, every time when you're switching on your lab kit, I believe you sort of see this little message, something like CSE 369 or EE 271, or something like that, that gets displayed on the little 7-segment display. And one way to realize this, of course, is that you have to, the information that you're seeing is stored in a memory. And the way it's displayed is by essentially having a counter. Let's say a counter here with a clock. So maybe it's a 5-bit counter. Counts from 0 to 31, and that may be connected to a memory, and specifically it's a 32 by 7 memory. So there's inputs here A0, A1, A2, A3, A4. The counter generates a number. That's essentially the address. So you're basically, by going through this, by cycling through the number store, or just counting upwards from 0 to 31 and again and over, you're cycling through all the addresses in this memory, and in each location there's some information stored, and specifically what's stored is information about which subset of this 7-segment display you want to activate to display a number. So the outputs here D6, D5, D4, D3, D2, D1, and D0. And of course the wire here, D0 connects to L0, etc. And then for completeness, on this last slide here, I'm also giving you just some Verilog code, specifying in memory, obviously the core of this are these lines here. So always at star data out is memory of address. So basically what's stored at the given address is what's read out, and always at the positive edge of the clock. If writing is enabled, then I'm putting new data into the memory.